We're solving problem 1 from the 2024 AIME 1. Every morning, Aya goes for a 9-kilometer long walk and stops at a coffee shop afterwards. When she walks at a constant speed of s kilometers per hour, the walk takes her 4 hours, including t minutes spent in the coffee shop. When she walks at s plus 2 kilometers per hour, the walk takes her 2 hours and 24 minutes, including t minutes spent in the coffee shop. Suppose Aya walks at s plus 1/2 kilometers per hour. Find the number of minutes the walk takes her, including the time t minutes spent in the coffee shop. So we can write an equation for time for this problem. So the actual walk, it's going to take her distance divided by the rate. So in the first case, when she walks at a constant speed of s kilometers per hour, distance over rate, that's 9 over s. Add the time in the coffee shop, you get 4 hours. Now, for the second case, you can do the same thing. 9 over s plus 2, because s plus 2 is our new rate, plus t in the coffee shop is 2.4 hours. Now you can subtract this one from this one to get 9 over s minus 9 over s plus 2 equals 1.6. This then becomes a quadratic where you eventually get 4s squared plus 8s minus 45 equals 0. This simplifies to 2s minus 5 times 2s plus 9 equals 0. And then, well, this is our only logical solution, because if this was a real solution, then she'd be going at a negative speed, which is impossible. You can't go at a negative speed unless if it's relative to distance, but that still won't make any sense because she'll be going the other way. So for this, s is equal to 5 over 2 or 2.5. Now you can just plug this into one of these equations to solve for t. So t is equal to 0.4 hours. So now what we want to do is solve for s plus 1/2. We know that this, or how long it would take her if she walks at s plus 1/2 kilometers. So really, it's we want to solve for this right here. So s plus 1/2 is 6. So, or no, 6 over 2. So this is 3. And then 9 divided by 3 is 3. And then we substitute in the t value we got, which is 0.4 hours. So we get that it takes her 3.4 hours in total if she walks at a pace of s plus 1/2. S plus 1/2 kilometers per hour. But we want to convert to minutes. So when we do that, we get 204 minutes spent in total, and that is our answer. We're solving problem 2 from the 2024 AIME 1. There exist real numbers x and y, both greater than 1, such that log base x of y to the power of x equals log base y of x to the power of 4y equals 10. Find xy. Now this problem requires the use of logarithmic properties, and it might seem really complicated that we have powers in this part of a logarithm. So the first thing we can do is literally just get rid of them. We know that we can just do this by changing the power to multiplying it in front. So likewise, this one here becomes x times log base x of y equals 10. And then for this one, we do the same thing, just bring the power down. So 4y times log base y of x equals 10. And now this requires some very interesting insight. So these two are 10, and we want to find x times y. Now if we multiply these two together, we have an xy, but these two are a bit of a problem. However, we notice that there is a logarithm rule, like you might remember, there's a logarithm rule log base A of B times log base B of A is equal to 1. So if you multiply these together, these log terms cancel out because when you multiply them together, they're 1. So 4xy times log base x of y times log x base y is equal to 100. 10 times 10 is 100. This is just 1, and then divide the 4. xy is equal to 25, and that is going to be our final answer. We're solving problem 3 from the 2024 AMY 1. Alice and Bob play the following game. A stack of N tokens lie before them. The players take turns with Alice going first. On each turn, the player removes 1 token or 4 tokens from the stack. The player who removes the last token wins. Find the number of each of positive integers n less than or equal to 2024 such that there's a strategy that guarantees that Bob wins regardless of Alice's moves. So for this problem, we can just start trying out integers n, numbers of tokens, and then we want to see if there's a common pattern or anything. If Alice wins, like if there's a pattern in which Alice wins. So let's just call W where Alice wins and L, Alice loses. So if there's 1 token in the stack, Alice can just take it, so she wins. 2 tokens, she loses, because she has to take only 1 token, and then Bob takes the other, and he wins. For 3, Alice wins. Now for 4, Alice also wins, because she can just take the 4, right? For 5, Alice always loses. And as you go on, you're going to keep on seeing a clearer pattern. But these first 5 basically dignify that she loses at 2 and 5 tokens. Another way we can rewrite, well, if she loses, then Bob wins. So another way we can rewrite this is that Bob wins 2 out of 5 times when the number of tokens is congruent to 0 or 2 mod, 0 or 2 mod 5. You can keep on testing this, but this is always true. Bob has a 2/5, 2 out of 5% chance of winning. Like if there's a strategy that ensures that he wins and that they both play like the best moves. So, what we do is we take, so we have Bob wins 2/5 of the time from 1 to 2020. And why I say it's 1 to 2020 is because 2021 to 2024 only has one case where Bob wins, 2022. 2021, 2023, and 2024, they all ensure that Alice has a way to lose. Or no, to win every time. So what we do is 2/5 times 2020 plus the 2022, so that's one number, is equal to 809. There are exactly 809 values of n where Bob is guaranteed to win if he and Alice both play their best moves. We're solving problem 5 from the 2024 AMY 1. Rectangle ABCD has dimensions AB equals 107 and BC is 16, and rectangle EFGH has dimensions EF equals 184 and FG equals 17. Points D, E, H, C, and F lie on line DF in that order, and A and H lie on opposite sides on line DF as shown. Points A, D, H, and G lie on a common circle. Find CE. For this problem, what we want to do is we want to just find a pair of similar triangles that can aid us in finding CE. But first, we need to use those similar triangles to find that little sliver DE. So if we draw it out like this, what we can notice is that we have the angle. We have angle. We're gonna have angle G A G A H is equal to. Wait, no, not G A H. But we want to find a set of angles that really helps us proving that there are some similar triangles that we can work with. So we have angle GAB is equal to 90 degrees minus angle DAG. And DAG, we can even simplify that more to 180 degrees minus DHG or GHD. This is an angle. So this is this GAB is equal to angle DHE. Thus, we know that the triangle DHE is similar to the big triangle A, G, and T, where T is, like, if you keep drawing the segment FG down and AB to this way, it's the intersection of that. So, what we can do with that information, let's call that tiny DEX. Then, if we can use some ratios. So DE over EH is equal to GT over AT. So DE is X, EH is 17, GT is equal to 17 plus 16, which is 33. And then AT is simply 184 plus X. After this equation, you solve for X, and X, we get that X is 3. So CE is simply 107 minus X, or 104. That is our answer for this problem. We're solving problem 6 from the 2024 AMY 1. Consider the paths of length 16 that follow the lines from the lower left corner to the upper right corner on an 8x8 grid. Find the number of such paths that change direction exactly 4 times, as shown in the examples below. These are the 2 examples they have, where they do indeed obviously change direction 4 times. So, for this problem, what we can do is we can split the movements into movements where it's going right, the path is going right, and movements where the path is going up. So, if we have that, then we have only 2 configurations, or we have 2 possible basic configurations when it goes right, up, right, or up, right, up. These configurations result in like making 4 turns, basically, or these result in having 4 turns. So we can just take the first case and then multiply it by 2, and then so you multiply 2 to our answer. And then for the up cases, well, we see that for up cases, we can set the length of the first up, like the length of the first time the path goes up to A, and then the second time the path goes up to B. And we know there's 8 of them. It has to go up 8 in total. So so we can just sum A and B. We know this has to equal 8 because the added length of the 2 instances of it going up here has to add up to the total height of the 8x8 grid, because we want the path to go from one corner to the other corner. So we therefore have 7 resulting pairs of A and B. we have 1, 7, 2, 6, dot, 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 all the way to 6, 2, and 7, 1. That's a 7. So, we can just, from R, we subtract every one from it, and then we can just use stars and bars. Stars and bars technique gives us 7 choose 5, which is 21. So our answer is going to be 7 times 21 times that 2 from earlier is equal to 294. That is our answer for this problem. We're solving problem 7 from the 2024 AMY 1. Find the largest possible real part of this equation up here, where z is a complex number with z absolute value of z equals 4. Here I is the square root of -1. The first thing we can do here is we can simplify it a little. So we know that z is a complex number, so we can just stop there. The standard form of a complex number is a plus bi, so we can just let z equal a plus bi. Then this equation becomes 75 plus 117i times a plus bi plus 96 plus 144i over a plus bi. We can do something, we can manipulate this side to get us, and we can call this very complex number w, just to make things simpler. W is equal to 75, that's a weird 7, 75 a minus 117b plus I times 117 a plus 75b, and then for this side we can factor out the 48 on the top, so 48 times 2 plus 3i over a plus bi. Now the next steps we do is all of this doesn't really matter. It's just simplifying, but we have to find a really unique way of simplifying that gets rid of this denominator. So basically, if absolute value of z equals 4, z squared is going to be equal to 16. So what we can do is we can apply difference of squares here. If we multiply by an a minus bi, it would cancel out, leaving an a squared plus b squared, which is equal to z squared, or 16. So I don't want to write all of this out again because it's the same, but right here, if we do 48 in the parentheses 2 plus 3i, a minus bi, and then divided by a plus bi times a minus bi. All of this simplifies, but I'm going to write it a little bit smaller now. 48 times 2a minus 3b, that's plus 3b. And then on the top we can factor out the I, and this becomes 3a minus 2b, and then divide this by a squared plus b squared, which we know is 16. So then, since 48 can divide into 16, we have this equation, and then we can simplify it out with all of this, with this up here, since it's still here, it's just dots, put it as dots, I don't want to write it out again, but you can just simplify it down by subtracting and adding like terms, so you get that w is eventually equal to 81a minus 108b. Now here, what we can do is we can use sine and cosine for this. So we let a be equal to 4 cosine of theta and b equal to 4 sine of theta. Then the equation becomes 324 cosine theta minus 432 sine theta. And then we can use the Cauchy-Schwarz inequality. I don't know if I'm pronouncing it right, but use the inequality. And it's 324 squared plus 432 squared times cosine theta squared plus sine squared theta. This has to be greater than or equal to all of this squared. So 324 cosine theta minus, I'm just going to write it down here, 324 cosine theta minus 432 sine theta squared. Now here, I know this looks weird, but I don't have really space to write this, so this is greater than or equal to this. So we can get rid of the square. We get 540 squared times 1 greater than or equal to 324 cosine theta minus 432 sine theta. And right here we have our answer. Because we want to maximize the value, our answer is simply going to be 540 for this problem, and we are done. We're solving problem 8 from the 2024 AMY 1. 8 circles of radius 34 can be placed tangent to BC of triangle ABC so that the circles are sequentially tangent to each other, with the first circle being tangent to AB and the last circle being tangent to AC as shown. Similarly, 2024 circles of radius 1 can be placed tangent to BC in the same manner. The in radius of triangle ABC can be expressed as m over n, where m and n are relatively prime positive integers. Find m plus n. So the first thing we can do here, this is a really bad drawing of this triangle, but because there are two different cases, right? Case where there's 8 circles and all the circles are tangent to these points, and then there can be 22 circles that are tangent to sides AC and AB. So we want to find the relationship between those two cases. Let's just visualize this second case where the triangle is made up of 2024 radius 1 circles. So if we go like this, just gonna put a dotted line here, but it's gonna be tangent something like that. Now what we can do in this problem, if we have these 2 points, right, these 2 centers of the ends of the circles with radius 1, and then we draw a vertical like this, what this does is this splits BC into 3 parts. This long segment, and then these 2 segments. So this one, we're calling from the center of the last circle on the right to point B, have length lowercase b, and then the length from point C to the center of the circle of radius 1 on the upmost left is A. So we could find the sum of BC now. But how does A and B relate to this case right here, where the radius is 34 times bigger? If we do the same thing, we have the center of this circle and the center of this circle about. Well, this is going to have some correlation with this value of B, similarly to how this will have some correlation to the value of A. But these are similar triangles because these are 90 degrees and the angles are all the same. So therefore, they have to have a scale factor between those two. So because the radius of this circle is 34, all the lengths on these triangles will be 34 times that. So right here, oh wait, this is B, and this is C. Oops. But this length right here, this length will be 34 times A, and this length will be 34 times B. We therefore have two different ways to express the length of BC. So we have BC is equal to, if we take this case, right, starting from this circle to this circle, you have 22 circles. But then you're excluding the halves of the circles that were cut in half. So you do 2 times 22, because the diameter of each circle is 2. And then you have to add these halves from the circles, from like the cut in half circles, and then you have to add the value A and B. Similarly, with this case here, we can do 6 times 68, because that's the diameter of the circle in that case, and then you add 34 plus 34 plus 34A plus 34B. Now, once you solve the systems of equations, you get 1190 over 11 equals A plus B. Let R be the radius of the circle that this triangle is in, right? If R is the radius, then that means length BC, that means it must equal to, we can express it in R times A plus B. Therefore, if we solve by dividing both sides by A plus B, we get that R is equal to 4096 plus 1190 over 11 over 1190 over 11. Therefore, eventually giving us 192 over 5. So 192 plus 5 is 197, which is our answer for this problem. We're solving problem 9 from the 2024 AMY 1. Let A, B, C, and D be points on the hyperbola x squared over 20 minus y squared over 24 equals 1, such that ABCD is a rhombus whose diagonals intersect at the origin. Find the largest number less than BD squared for all rhombuses ABCD. So for this problem, what we can do is, well, let's just assume AC is the asymptote of this hyperbola right here. That means that BD is automatically minimized, and that's what we basically want to work off for this problem. So if AC is the asymptote and BC is minimized, or no, BD. BD would be expressed as the line y equals negative square root 5 over 6 x. And we have this into that equation. Putting that into there, we get that x squared is 720 over 11. Now our desired value for this problem is going to be 4 times 11 over 6 x squared, which is going to be 480. Since this case cannot be achieved, that means BD squared, all cases BD squared is larger than this number. So this is the lowest number. Yeah, this is what we're looking for because it's the largest number less than BD squared for all rhombuses ABCD. That is our answer. We're solving problem 10 from the 2024 AMY 1. Let triangle ABC have side lengths AB equals 5, BC equals 9, and CA equals 10. The tangents to the circumcircle of triangle ABC at B and C intersect at point D, and AD intersects the circumcircle at P is not equal to A. The length AP is equal to M over N, where M and N are relatively prime integers. Find M plus N. So the first thing we notice is that this entire length is it's the asymedian of this thing right here, and let's just let M be the midpoint of BC. Because it's the asymedian, through similar triangles, we find that triangle ABP is similar to triangle AMC. Then, through the use of the median length formula, it basically just lets you find the length of median. So in this case, we solve for AM. AM is equal to square root 200 plus 50 minus 81 over 2. This equals square root 169 over 2, or 13 over 2. Next, through similar triangles, because we just found out AM is 13 over 2, because these two are similar triangles, 13 over 2 over 10, so AM over AC should be equal to AB over AP, so 5 over AP is equal to 100 over 13. 100 plus 13 is equal to 113, our answer for this problem. We're solving problem 11 from the 2024 AMY 1. Each vertex of a regular octagon is independently colored either red or blue with equal probability. The probability that the octagon can then be rotated so that all of the blue vertices end up at positions where there had been red vertices is m over n, where m and n are relatively prime positive integers. Find m plus n. Now, to start this problem, we can just start considering the cases of how many blue vertices there can be. There can be up to a max of 4 blue vertices and no more, because then it wouldn't be possible. So if we have 0 blue, we have one case. If we have 1 blue, we can rotate it 8 times. If we have 2 blues, we can similarly calculate this to be equal to 28. And then for 3 blues, we calculate 56 using the choose function. If we have 4 blues, we can split this up into cases. The first case is where we would have an octagon going like now the circles, the vertices I'm circling means they're blue. So this would only have 2 cases. The next case, if we have an octagon, hang on. If it's circled like this, it looks weird, but if it's circled like that, that only yields 4 ways to rotate it such that it works. And then we have 2 more cases that work. That's not good. So our next case is where, similar to this above case, these 2 circled, but these 2, instead of the bottom 2 vertices are circled. This yields 8 ways to rotate it. And then our final case we have to consider, this is the final working case. When you're doing the test, you just have to test things out. Our final really working our working case, it's like this, where all 4 of a half is selected. This yields 8 ways to rotate it. So the total number of ways to have red or blue vertices on an octagon is 2 to the power of 8, which is 256. We can then sum up all these numbers and divide by 256 to get m over n, and then we just add them. So we do 1 plus 8 plus 28 plus 56 plus 2 plus 4 plus 8 plus 8 over 256. All of this on the top gets us 115 over 256. And adding 115 and 256 gives you 371. So that is our answer for this problem. We're solving problem 12 from the 2024 AMY 1. Define f of x to be the absolute value of the absolute value of x minus 1/2, and g of x to be the absolute value of absolute value x minus 1/4. Find the number of intersections of the graphs of y equals 4g times f of sine of 2 pi x and x equals 4g times f of cosine of 3 pi y. Now for this problem, what we can do, this is definitely not recommended on the test, but if you can, that's good for you, you know? But this is a more like technical solution. Because we want to find the number of intersections on the graphs, what we can do is we can just graph it. So we want to graph 4g of f of x. You can do this on like Desmos, or you can try and draw it out, but it's not recommended. This is a graph that oscillates between the values 0 and 1. So it's we have to therefore bound it by 0, 0, 0, 1, 1, 1, and 1, 0. These are the points it's bounded by. It's a square. Unit square, you could say. And then you can just count the number of intersections there are, and by some counting strategy or another, you can come to the conclusion that there are 385 intersections for this problem. We're solving problem 13 from the 2024 AMY 1. Let p be the least prime number for which there exists an integer n such that n to the power of 4 plus 1 is divisible by p squared. Find the least positive integer m such that m to the power of 4 plus 1 is divisible by p squared. So, if n to the power of 4 plus 1 is divisible by p squared, we can say that n to the power of 4 plus 1 is congruent to 0 mod of p. Now we see here that the lowest number that can satisfy this is 17, because 17 equals 2 to the power of 4 plus 1. We can then call g a divisor of 17 squared. So we have that we have that n, our values of n are going to be in the form of g to the power of p minus 1 over 8, g to the power of 3 p minus 1 over 8, g to the power of 5 p minus 1 over 8, and g to the power of 7 times p minus 1 over 8. Here, well, we notice that for basically this to work, we have 17 squared has to divide into 2 to the power 4 times 17 plus 1 by LTE. Therefore, the values of n working for this, it basically is n cubed, n to the power of 5, and n to the power of 7. Therefore, we have our answers of 2 to the power of 17, 2 to the power of 51, 2 to the power of 85, and 2 to the power of 119. So, therefore, we can then from this deduct that this is our answer, 2 to the power of 51, and making it congruent by using modular arithmetic, we get 110 as our answer. We're solving problem 14 from the 2024 AMY 1. Let ABCD be a tetrahedron such that AB equals CD equals the square root of 41, AC equals BD equals the square root of 80, and BC equals AD equals square root of 89. There exists a point I inside the tetrahedron such that the distances from I to each of the faces of the tetrahedron are all equal. The distance can be written in the form m root n over p, where m, n, and p are positive integers. M and n are relatively prime, and n is not divisible by the square of any prime. Find m plus n plus p. So for this problem, we see that if you draw it out, the tetrahedron can be inscribed in a 4 by 5 by 8 box. Therefore, we can convert points A to D to coordinates on the three-dimensional coordinate plane. And that will help us solve this problem, right? So point A is going to have coordinates 8, 0, 0. B has 8, 5, 4. C has 0, 0, 4. And D has 0, 5, 0. So these are the coordinates for the three-dimensional plane. Now, what we can do is, well, there's this formula, right? I'm just going to write it out. V equals 1/3 RS. So volume equals 1/3 times R, which is the radius of the insphere, and S is the surface area. So we can kind of use this formula, right? Since all sides are equal, we can implement this formula and change it to our liking. So we do 1/3 times the plane ACD times H, where H is the height from plane ACD to point B. We can then find that R is going to be equal to H over 4. Then the equation of this said plane is going to be 5x plus 8y plus 10z minus 40 equals 0. So we can use point to a plane to solve for h. H is equal to the absolute value of 5 times 8 plus 8 times 5 plus 10 times 4 minus 40 over the square root of 5 squared plus 8 squared plus 10 squared. This equals 80 over the square root of 189. Therefore, when we solve for R is going to be 20 root 21, or no, this is just going to be our answer. 20 root 21 over 63, which is in the form that we want, because we have to convert it to this form, and then we just add these up. 20 plus 21 plus 63 is going to be 104, and so that is our answer for this problem. We're solving problem 15 from the 2024 AMY 1. Let B be the set of rectangular boxes with surface area 54 and volume 23. Let R be the radius of the smallest sphere that can contain each of the rectangular boxes that are elements of B. The value of R squared can be written as P over Q, where P and Q are relatively prime positive integers. Find P plus Q. Now for this problem, it might seem really confusing if you just approach it head on, but one of the insights that you can use for this problem is if you convert it to a number theory problem, and then it becomes sort of elementary. If we have three values that are coprime, P over Q, Q over R, and R, well, we can instantly denote that P equals 23. Then our equation would be 23 times R squared plus Q over PQ. No. Well, we can denounce that we can simplify it into something simpler. So we would have this over QR plus Q is 27. From this, we get that Q is equal to 4. So we have 23 over, or plus 4, plus Q. Oh, and no, it's not Q because we have a value for Q, and that's 4. So we have 23R over 4 is equal to 27. R equals 2. Now, for a cuboid inscribed in a circle, the radius is half of the diagonal. So if we have R squared is equal to, in parentheses, L squared plus B squared plus H squared over 4. R squared is then equal to 128 plus 529 over 64, which is 657 over 64. So then you just add these two up to get our answer. 657 plus 64 is equal to 721, and that's our answer for this problem.